I think we can slowly start. The stream is live on YouTube. So welcome everyone to the fifth session of our community Discord talks. Today our guest is RavenDB CEO, so I'm very excited to have Oren here today on our Discord. So yeah, Oren, you can start.
Awesome. Thank you. Thank you everyone for being here. And I'm going to geek out in this talk. And if you have any questions, feel free to ask them as we go along. And the reason I say that I intend to geek out is that this is basically a talk in which I get to speak about all of the really interesting things that we do that we never have a chance to talk about because we get lost in the details. So just, I think, exactly 10 days ago, we celebrated 15 years of RavenDB. This is since the time it was released the world, not starting development. That's even years earlier. And as I look back, I'm looking into some of the key changes that we had. And I think that the major change was in February of 2019 when the RavenDB 4.0 was released to the world. And this matters because that represented a really fundamental change from our perspective on how exactly we are, how exactly RavenDB is even built. And this happened because we hit a limit in the architecture that we had, and we have to re-architect from scratch. This is the release date. We actually started working on that in 2015. So we're talking about 3 years of development just to get to the point that we released. Earlier this year, we released vector search and AI integration into RavenDB. And very soon we are going to have GenAI integration, the ability to make your data think directly inside of your database. And there are some AI goodies that I'm not at liberty to discuss right now, but I'm super excited about. The topic of this conversation, this talk, is none of that. Because what I'm actually going to talk about today is RavenDB 8.0. And this is scheduled for next year. The reason it's scheduled for next year is because we had made some amazing changes into the guts of RavenDB. A storage engine that we use to store the data on disk is called Voron, and we remodeled the internal architecture to a significant degree. The reason for that is that we wanted to have better performance. And if you make that sort of a drastic change, especially for a database, we have to make sure that this is absolutely running. And because of that, we basically need to give it a lot of time to percolate and test it and try to hammer that every which way. So let's talk about this. When we talk about performance, this is mostly what we talk about. We're talking about taking a piece of code. By the way, this is a really significant piece of code. This is how we load a document from the disk and making it faster. This is the result of days or weeks of work. You can see that we moved from 450 operation to 480. This is on a per millisecond basis. So it actually comes to a really significant performance improvement, because that means that we can do, instead of 450,000 operations per second, 480. So another 30,000 operations per second that we can do. This is the really core aspect of RavenDB. So something like this, when we saved over 6% of the runtime, this is a cause for celebration. I'm not talking about those kind of changes today. I'm talking about stuff that can radically move the needle. So let's talk about Voron. And Voron is our storage engine. This is how RavenDB talks to the disk. So we actually started building Voron a very, very long time ago. I went to look at the code base, and we started working on that on 2013. In 2014, we had released that as an additional optional storage engine for RavenDB. And in 2015, we actually started revamping the entirety of RavenDB to sit on that. And 2018, that's the release, and this was the backbone for everything, for how we did store data on leads, for how we did indexing. Everything at all was sitting on Voron, and Voron was heavily optimized for our scenario. One of the things that we did, which I think went really well, was to ensure that as we write Raven, we modify Voron to fit it, and vice versa. So there was a very strong tie between those two components and a very good sum of all parts that gave us both really rapid development and really good performance. I want to have a honorary mention here for Munin. Voron was not the first storage engine that we wrote. There was also Munin, which is an LSM-based storage engine, which was scarce to never actually get to real production situation for a very long time. Munin was the storage engine that you use if you wanted to run RavenDB in memory, but now Voron takes care of it. I haven't seen or heard about Munin in about, 13 or 14 years, but I still remember 3 weeks that I spent trying to debug race condition in there. So it's somewhat cursed. Something to note about this timeline. Notice when we start building Voron. And around this time, Voron was stable. We still made, changes and updates. Orgs is completely built on Voron, etc. But the backbone, the way that you work with Voron has been relatively stable since, I think, early 2016, something like that. So let's talk about the sort of design decision that we made back then. So 2013, 2014, we built the design. 15 and 16, we pretty much settled on everything. And it worked. So there was no need to touch that. But there are two things that happened that were really interesting. And this is horrifying to say, but first of all, kind of hardware that we run on today versus what we used to run. I went to look at the numbers, and this is a $6,000 a month machine in 2013. 16 core, under 120 gigabyte RAM. And this is what about one half of that would get you today. So 64 cores at 256 gigabyte of RAM. And if you want to try to keep, roughly the same price point, 192 cores and 768 gigabyte of RAM. That is a huge difference in the way the system works. What resources do I have? What can I do? What's the environment in which I'm running? And another really important aspect is that I think in the 12, 13 years since we wrote this code, we learned quite a bit about hardware, software, how to build more efficient systems. But we never actually had a reason to revisit that until we tried. We were in the middle of doing some benchmarks to see how the system behaves. And we ran what I believe is a very simple benchmark. 5% writes, 95% reads, and let it rip. And we did that on a machine with 195 core. So 192 cores in the system. So from our perspective, there is a very high expectation to get really good numbers. We got some nice numbers from that. But, under load, we noticed that the CPU is really struggling. We didn't really see the kind of better performance that you see when you scale the machine up. In fact, we saw that it started even going down. When we start looking into that, you can see here this horrifying image. This image is horrifying because it represents about 6 months of work. Just this thing. Let's talk about why exactly this is the case. 50% of the time that we run, 50% of the time that we need to open a new transaction is spent on lock management. More specifically on a spin lock, which means that we are burning CPU cycles. And the more CPU cores we have, the slower we become because the contention is higher. That was absolutely insane. Then we start looking deeper into what's going on. What is it that caused this? And we realize that we had a dispute of code during the opening of a transaction. So very early on, we had to create a lock. Whenever RavenDB commits a transaction, we have to update some state in memory. And in order to ensure consistency, we have to do that under a lock. So in RavenDB up to 7x, when you're committing, there is a very short period of time in which new transactions are not running. In almost all cases, except silly benchmarks like what we're trying to do, this doesn't matter. This doesn't matter because you're not actually sitting there doing really, really cheap reads all the time. You have some work to do. This scenario that I'm talking about here, this is load document by ID. This is about the cheapest operation you could do in RavenDB. So the problem was that the cost of opening the transaction dominated the entire operation because we also have a lot of writes that would always contend to that. So we have, one core that is busy processing writes, and 191 cores that are trying to open a new transaction, and all of them would hit this lock when we commit a transaction. That would mean, in turn, is that all of them would start spinning, burning a huge amount of CPU cycles. It sucks so much. Again, I'm talking to you about a design decision that I made in 2013. 4-core machines were not even that common. So in the guts of Voron, we have a prevent new transaction call, and that creates a convoy. Now, I want you to notice how old this guy is. It's absolutely insane. 12 years ago, this is when we actually made this change. Now, there is a problem with old code like that. Old code like that is code that works, that we have tested, that we verify, that we know all the edge cases of. Understand how it fails, understand what it works. Changing old code is really, really scary because this code has survived production. So let's talk about mutable state and what it does. What is protected by this lock? Pages, which is a Voron term for open files, scratch files, scratch buffers, which is memory access, so memory allocation, deallocation. And then we have this lovely event. This is being raised while there are no new transactions, and we are using that to modify other state across the database. Only, small unimportant things like what is the status of the cluster or the Lucene index structure and all bunch of other stuff like that. That actually led to a huge problem because if the more that we did here, the more time this phase took, in which I cannot open new transactions. Now, going over the code, there were 18 different places where we used this thing. And this has been around for 9 years, and it accumulated a lot of behavior and features. That was a mess to fix because it is restructuring of the very belly of the beast. So I mentioned that it took me months and months. So here you can see this is one of 4 that was required to make this change. The problem with that is that, and I just love this. This was so big that if you loaded this PR a few times, there is 1 in 8 chance GitHub would just say, I give up. I'm not even trying to load that. Go away. And I actually try really hard to get to the point that there is a net 0 additional code. But at some point, it was nonsense. The key aspect here was to drop the notion of mutable state. Instead, we have this guy, this record. And this record holds the current state of the system. And this is, notice that we're using here a C# record, which is immutable. So, and everything in here, by the way, is also either read-only, like value types, like tree root header is a struct, or this is immutable dictionary that we cannot change. So the whole idea is that now we talk about this record as an immutable aspect. And when we commit, we don't need to do any coordination between threads. We just update this guy, then we're done. There is no coordination between threads. And if there is a new transaction that is being opened while I'm running this, it's going to, one of two things is going to happen. First, I'm going to get the old one when I don't care. It's an old transaction that I would have gotten if I happened 1 millisecond earlier anyway. Or I'm doing that afterward, in which case I'm getting the committed view of the system. So either way, I'm okay, and this is going to work great. Another thing to notice, look when it was merged. August 2024. And now in May 25, and the release date, the planned release date for that is Q1, Q1 of 2026. They're going to take over a year just for stabilization of testing of this chain. The major benefit that we have here is that now there is no coordination, no complexity, and no need to even think about it. Everything about the system is now centralized here. That made the overall architecture much, much simpler. And we just published the new values, and then we're done. No locks, and the scaling is linear with more cores. Again, no locks, there is nothing for you to do. It does represent a huge problem for us. Previously, one of the things that we use this log for is to use for reference counting. Or I have a transaction that now looks at this particular file. How do I ensure that I'm not closing this file while another transaction may be trying to read for that? Or memory buffer, or anything like that. So that was a huge problem. Then again, that was also another cause for contention, for not being able to scale to many, many cores under this particular scenario. By the way, I have to make a note on this. The reason that we didn't notice that is that this is a really real scenario. Because most of the time, transactions and requests are going to do some interesting amount of work. Execute a complex query, submit data to be saved, those sort of things. The scenario that we tested was the absolute worst thing for this particular setup. We're doing really, really cheap cost, really, really cheap calls, and the cost that we're paying is just the overhead of everything. So let's talk about how we manage resource management with concurrency without locks. And the idea here is that there is already an entity in place to keep tracks of that, keep track of references and when we need to clean it up, etc. And that's a GC. The .NET GC is already guaranteeing to me that it will call the finalizer when no one is looking into that. So the whole idea is, let's go back here. For example, this state, this is a finalizer value. If I have a transaction that needs to hold this state, this basically holds the a file handle for this transaction. And as long as there is a reference node, as long as that old transaction is running, that state is not going to be recoverable, and I can keep on using that. But if GC is there, it said, oh, I can call the finalizer, that is really good indication no one is looking at this. So that solves the problem really nicely. That leads to a different problem. How do we get deterministic resource release? How do we actually manage to ensure that, oh, I'm shutting down my database, all of the handles are closed, all of the memory is discarded? And the answer to that is that they're actually keeping a weak reference to all of the resources that we no longer hold. And if we dispose the database, we immediately dispose them. Because if you dispose the database, you're no longer using any transactions. So that's cool with this regard. But it also means that I don't need to do any tracking. I don't need to worry about that. For normal operations, I get to, oh, I'm using this file, and then I'm not using that, and then the system will just clean it up for me on the fly. I was kind of afraid of making this change, but we tested the performance of that. That turned out to be a really, really beautiful thing. It was, wow, it works, it's and the end result is that we could delete so much code, and a huge amount of complexity just went out the window. Right, that is actually a concern for us. And one of the reasons that I'm doing talks about how we did it, to make sure that people are aware of the behavior in the code that is not there. Because we are utilizing the GC, but there's a huge comment there that says, oh, this is why, and this is how it does that. So we understand how it works, in 5 years or 10 years. Remember, our code base is now approaching 20 years old. Something that longevity of the project, something that I care very much about. Okay, so the end result is that we have no more locks in this area. And from an architectural standpoint, this is so much better. It fits, it flows, it just, wow. It also, so far, we had to do no changes to the disk. All of that was just re-architecting the way that RavenDB itself is working. So from your perspective, you start using that, and there is no change whatsoever. Oh, wait, it does get faster, but that's it. But most of the time, I don't think that you will notice it that much because we are plenty fast enough already. Okay, so we're already starting to touch large pieces of RavenDB, Voron, and then we started looking into other aspects. How do we use the disk, and can we use it better? Let's talk about how Voron is using the disk. And there are actually 3 types of files that we use, and 3 different or 3 or 4 different ways to actually write data in RavenDB. So the most obvious thing is the data file. If you go look at the raw directory that store your RavenDB database, you see there is a raven.voron file. We call that the data file. And this file, we're doing random reads and writes to that based on whatever you loaded. Journal files or log files are how we write, how we commit transaction. This is the write ahead log, write ahead journal. This is how we ensure that when we tell you that the transaction was committed, even if we just had a power outage or some error or something, we can safely recover. The journal files are read-only, pre-allocated. Sorry, the journal files are write-only, pre-allocated, written to using a direct I/O, and they're only ever read on recovery. So this is a drastic different way in terms of what I/O use and what you're doing with that, and anything else that we do in the data file, which is much more fluid and based on what the user is doing. If you're always touching the same set of documents, then we're only touching that portion of the data file. If you're spread around, and we are going to go wherever we need to and basically do random reads and writes. Then we have something called scratch files. Scratch files are basically they are a workaround for Linux being stupid. And Linux has something called the out of memory killer. If you use too much memory, and Linux would basically say, oh, I told you that you can use this memory, but you actually cannot, and now I'm going to kill you to reclaim memory because someone else needs that. So it turns out that this only applicable for something called anonymous memory, what you get from malloc. But if you used memory map files, and instead of killing your process, and Linux is able to throw that data into the disk, and then you can recover from that later. Why does it matter? Voron is something called MVCC, multi-version concurrency control storage engine. And the idea here is that when you modify a document, you're not immediately writing to the data file. We cannot do that because data file may be currently read by another transaction. So we write that modified page into the scratch buffers. And only when you commit, we're going to take those modified pages, those documents that you change, and write them to the journal files. And at some later point in time, we'll copy them from the scratch file to the data file. So the problem here is that if you have long-running transactions, such as, for example, a backup that is running, at this point, you will not be able to discard, write this data to disk because the backup is still running really from the disk. So we have to wait for the backup to complete. And at that time, all of the pending modified pages that you have are going to still reside in the scratch file, which means that we have to use more memory. If we use memory map files like in the scratch files, then it basically gets schlepped to disk and we don't care about it. It just works. So let's talk about the kind of IO patterns that we have here. For scratch files, ideally, this means that it's only done in memory. Unless there is a memory pressure, we never have to write it to the disk. Journal files, this is how we commit the transactions, and we basically take all of the modified pages in the transaction, lift them, compress them, and write them to the journal file. We are typically talking about very, very small amount compared to how big your data is, because we are doing diffs, we are doing compression, or much of stuff like that. Then we have something called a flash. This is where we take the data from the scratch file and copy that to the data file. This is done when the MVCC infrastructure tells us that no one is looking at the areas of the disk that we have. This can merge writes for multiple transactions at the same time, and this also happens mostly at random because this again depends on what you did. Finally, we have in process in which we are writing from. We are effectively flash process is writing to the page pool. We're writing to memory, not to the disk. And we say, okay, let's take all of the writes that happen to the data file, and then we are going to write it to the disk to ensure that it actually hit the disk. After we sync the data file, we can delete the journals because now we know that we don't need to recover from that point on. In some other database, this is called the checkpointing system. Checkpoint, and then we can delete all of the journals. Okay, so let's talk about flashing and a really, really embarrassing mistake that I did. We need to copy the data from the scratch files to the data files. So this is MVCC, no one is looking, and then we can write. When I built Voron for the first time, I ran into a bug with Windows. It's not even a bug, this is worked as documented. The basic idea is that if you're mixing file IO, memory map IO on the same file, and Windows is not going to guarantee that this would be coherent. What does it mean? It means that Windows is going to say, hey, that data just wrote to the disk using the file IO. If you try to read it using memory map files, it will give you something else, not necessarily what you just wrote. And the reason for that are pretty complicated, related to internal structure of Windows, but this basically sucks. Now, Linux does not work like that. Linux ensures that if you write through file IO, then all of the memory map files are seeing the same thing. Turns out that, and this had a huge impact on the design of RavenDB, because I couldn't use file IO to write to the data file during the flash stage. I had to use memory map IO. Memory map IO has some interesting limitation that we'll discuss in a bit. So it turns out that I was actually wrong. This behavior is documented globally, but it actually only applies to unbuffer IO. If you're using direct IO, if you're using normal buffered IO, there is no problem. So this is not even relevant. Now, I don't know if it goes through how excited this makes me feel. Also kind of stupid, because that was my mistake. But this is a huge thing for us. Why do I care? I mean, I have a workaround. It works. Well, let's talk about the difference between those two. Okay. So when we do memory map IO, I have, and I'm going to write to the data file. Well, I have to read it first. Look at this. If I'm doing write to this mem1 or writing this buffer, well, the way that it works is that for each one of the pages that I touch, I may have to hit a page fault, which would then have to read it from the disk, and it's synchronous. And this doesn't actually write. This just mark the page at the memory table level, which is very deep in the guts of the CPU. We're not even talking about operating system level. We're talking about the CPU and the memory management unit. Mark it as modified. And the error handling is basically go die. This is what you get. With file IO, if I write to a complete block, or complete page, which is what I'm doing, I don't need to read from the disk because I'm replacing the full block. I can use async operations. I still, I'm not writing to the disk. I'm writing to the same page pool or the page buffer that the memory map IO is doing, but it also give the operating system immediate hint that, hey, I modify this. This is actually really crucial. When you write using memory map IO, the file system needs to go and scan those memory mapping to know that it needs to write to the disk. And if you're using file IO, it already knows that upfront. Another really important aspect is the error handling, that I get immediate error from the file system. Let's talk about how this actually works. Okay, so here is what I end up implementing. We have now four ways in which I can write to the disk. There is the memory map IO, like we previously did. Then we have file IO, normal file, or like write file or write system call. But those are not the only options. I now can use vector IO, write V in Linux or POSIX, which allows me to take multiple distinct buffers from the scratch and write it to the disk in one shot. So if I have 4 different buffers that I had that are consecutive, I can now write them to the disk in one IO operation. That can save you quite a bit of time and trouble. Finally, we can use IO ring to do even more than that and just push everything to the kernel and let it handle it by itself. We implement that. That's right now in 8.0. Based on your version in your system, etc., we'll auto-select the best option for. So that had a major impact on performance because now flashes are able to do a lot more. It also means that I don't have to fear that much from page faults and how those things are working. Let's talk about what it actually does and what's going on. So this is the write to memory, not to disk. This is the page case, page buffer, etc. When we write, we don't write to the disk, we write to the memory, and this is super, super fast. If we don't hit a page fault, there is no cost to that. No syscall, nothing. The problem here is that if you hit page faults, then that really, really sucks. And finally, we have to scan the page tables to figure what's going on. This actually ended up being something really interesting because this means that in terms of IO operations, we defer things by a lot. What do I mean by that? It means that I just wrote, 10 gigabytes through a flash. Well, the operating system have no idea this just happened. At some other point in time, the kernel will start scanning the memory mapping and says, oh, those pages are changed. Let me write those to disk. And this is actually apparently something that we relied on to defer writes to a later point in time. With vector IO, we reduced the number of system calls, but we also let the kernel know that stuff happened. So instead of having to wait until, I will discover something, it can start streaming data to the disk as soon as it hits its limit and not when it's discovering that when it may have exceeded that. Finally, we have the IO ring where we save on the number of syscalls, but same set of optimization is applied as with vector IO. Now, this is specific for .NET. One of the problems that we hit is the difference between page faults and native calls. Page faults, especially on a loaded system, can take a while to run. We have scenario where we see a page fault taking 10 plus seconds to operate. This is horrifying. The reason this is horrifying is what happens if I have a page fault, which can happen at any given point in time. The .NET GC is not, or the .NET framework and runtime, etc., is not already this happened. From its perspective, that thread is stalled doing something I don't know. And if you have a GC that needs to pause the thread to be able to collect the word cycle, this means that it cannot do that and it has to wait for this thread to come back from this page fault. So now you have a single page fault impacting the global system because now it holds everything else. Now, if you're doing a native call, like a syscall or IO or a syscall or a IO ring or whatever, and at that point, there is a very explicit transition. The GC can usually just go and says, I know that you're not going to touch any .NET code. And I put a note in the thread block that says, when you come back from this, don't continue executing, wait for me to release you. So that means that if I have a 10-second IO call, the GC happens, while this happens, I don't have to fear from a complete blocking. This is a complete accident of this change. This is actually a really important aspect. Okay. So another aspect that we have here is that how we use the IO ring. And the interesting thing about this is IO ring is actually single threaded, which is funny because this is meant to give you better async operation, etc. But this is basically just a queue that you operate on. And the assumption here is that this queue is owned by a single thread. So, in a big RavenDB system, I may have literally hundreds of files that I need to read or write to. But the way that it works is that if you open hundreds of IO rings, one for each one of those files, this is going to be really harsh on the kernel. because it needs to schedule things between all of those, and many of those resources are IO-ing local. So we have kernel tasks and things like that. So from my perspective, if I'm using the IO-ing, I'm using that. By the way, I haven't discussed that, but IO-ing is used here for flashing and for sync. So those are background operations. I don't care that much about them. So I want to let the kernel figure it out, do the best thing that it does, do the best thing that it can do. And that means that now we have a single IO-ing for the entire process, which handle everything for that. And because IO-ing is async, I don't care. I may have many on-flight operations, and we're good with that. This is the API that we have to write to the data file. This is the handle of the data file. Here are the pages that I want to write and where I want to write them, etc. Notice that this is a synchronous API. This is important because even though IO-ing itself can do async operations, the design of Voron says that when I submitted these changes to this to happen, I need to wait for them to complete. So we are not asking in this regard. Practically speaking, this doesn't matter. The reason this doesn't matter is because I have multiple databases running at the same time. I have indexes that are running at the same time. So all of them are actually thinking inside this team. Okay. I see that there are comments going on while this is happening that I completely didn't notice.
It's nothing. I just wrote a comment that if anyone has any questions, you can feel free to ask about anything.
Okay, so if there are any questions about what I'm talking, please raise them when this happens. I'd love to talk about them right now.
Yeah, I'll let you know.
Okay, thank you. Anyway, so we're basically doing that by submitting and waiting for this to happen for that particular operation. To may have multiple concurrent operations running at the same time. There is another aspect here that is not related to the actual mechanics of Voron, but does relate very strongly to the mechanics of how RavenDB is designed. And that is that I want to be able to go and stop to break into a RavenDB instance in the debugger and see what's going on in the system. And that is really, really important. What do I mean by that? Why do I care that I can see what's going on in the system? Well, try to imagine that I'm going into a live system and I want to understand what's happening, what's going on. Well, I can hit back into the system, or I can say, hey, you know what? So here is the stack trace of everything. And this is a great example. Here we have in separate threads, each one of our indexes. So now I can look at, can you see, by the way, the Visual Studio?
Yes, we can see the stack trace. Yeah, the studio, RavenDB Studio. Yeah.
Okay, so now we can see that here, all of those threads. And this is important because that means, from my perspective, is that I have an owner for knowing what's going on. Or I can go and look into what's happening, what's going on, what is taking all of the CPU, etc. So contrast that with the scenario where we are running a async task or something like that. If the async task is running in the background, I have no easy way of seeing that. And from a production debugging support perspective, this sort of behavior is super important for our goal to be able to actually get good, reliable information from the system. So this is actually, the reason this is synchronous is actually overall architecture, and that the other pieces of the system require it to be this way because this is how it was written, 12, 13 years ago. Okay, and let's go. So far, remember, all we have done is change from using memomap.io using file, whatever is vector file, a write file, or IOing. With memomap.io, I don't really have a way of controlling what's going on. With direct IO calls, I have, which means something that is super interesting. Now I can mark different IO with different priorities. So when I write a committed transaction, it's really important for me that the journal write that commits the transaction has the highest IO. If at the same time I'm doing a background flash to copy data from the scratch file to the data file, I want that to have lower priority because I'm fine with this taking longer. No one is waiting for that. So now I have the actual ability to do that. To actually say, hey, go with low priority IO, and that gives us the ability to share more load on the same system. By default, RavenDB would run flashes and syncs to the data file as low priority IO. There is a configuration if you really want to, but that's it. Now, let's talk about errors and what it means. Let's say that I got an error writing something using memomap.io, reading something through memomap.io. What's the only thing that operating system can do? It can give me a 6 segmentation fault. That kills the process. But if I'm using file IO, there is a channel for me to get those errors back. Try to imagine what this actually means. It means that now I have the ability to handle IO errors. That sounds like a really stupid thing to do because you know what? I'm fine with if the disk is bad, I want to crash. And in fact, for certain errors, if I'm failing to write to the disk, RavenDB reaction is to trigger a crash intentionally. Because at that point, I don't know what happened to the disk, and I have to run recovery from scratch to go back into a known good state. But let's talk about what happens. When you write data into a RavenDB, you write that into the system, write it into the file. What happens when you delete data? When you delete data, we are basically going to just mark it as deleted inside of our system. This is what this looks like. Here is some data, and you can see that there is some data here that is marked as free. If I would go and delete all of the information inside this database, you can go here to the data and see that, well, it didn't free much because I didn't have enough but this is free space that is managed internally by Voron. If we would now start writing more details, it would fill up this space for asking for more disk space from the system. Try to imagine that you just wrote, 16 gigabytes of data, and now you remove most of those. You're still taking 16 gigabytes of data. But because we manage that internally using our free list, what happened is that we can use advanced file operations to do something called hole punching. They're going to tell the operating system, hey, this section of the file, I give it back to you. The overall file size is still, 128. But the size of the file on disk, the size that we take, is now only 92, 96 megabytes. Now, and that means that the operating system can reuse this disk space for doing other stuff. You don't have to do anything for this to happen for you. Just works. Now, we couldn't do that before because of error handling. What happened if your database is 16 gigabyte? Now we want, and now you deleted, 8 gigabyte, which is fine. We can release that to the operating system. But what happens when that 8 gigabyte is being used by something else? We try using that. Well, if we would try to write using memory.io to that location, this would fail with out of this space error, which because we are doing a page fault on memory.io, we generate a segmentation fault and kill the process. With moving to using file operations, that means that we can detect that, we can manage that and says, oh, now I failed to write to the disk. This is a fatal error. Now, fatal error in terms of these operations. Then I'm going to force us into recovery. I will discard all of my scratch files. We try to recover more displays, etc., to get to move into that. You should note that we are still, in terms of disk allocation, still favor allocations. We will get 1 gigabyte at a time from the system once we hit a certain size, and slowly release that as necessary. This is because for most operations, we tend to have a growth and modification rather than mass deletes and writes all the time. Okay. So now, let's talk from the single storage engine aspect to looking at the entire system. Here's the test case in question. We have a database that has more than 1 terabyte of data. We are hitting it with a lot of writes, over 1,000 writes per second. And we are now running a huge number of indexes. Those indexes are now also going to have to do writes. So we have 1,000 writes per second for the documents that we're doing, and 100 indexes that are also doing that. In effect, we have more than 100,000 writes per second in this scenario. That's a lot. It doesn't sound like much until you realize, hey, this is what's actually happening behind the scene, because you look at the entire thing. This is the idea. Try to imagine that you have hundreds of those. This is writes that happen to the database file, and this is all indexes that cover various parts of that. In our scenario, those indexes would cover much of the system, so they will always be operating, always writing. And what we are actually looking at here is the document per second that we're able to write, and what is the latency of the write operations. And the key thing for us is the journal writes and the overall number of IOPS that we send to the database. And before I go there, I want to explain something about this. This is a RavenDB database. Each one of the indexes in the database itself is a Voron storage environment. Each one of them is operating independently and concurrently to one another. So if we have 1,000 writes per second, each one of the indexes is going to start cover whatever one of the indexes it has, and also write this completely independent of everything else. It's completely saturate the disk. So I set out to try. I got an NVMe drive. I tested that on cloud instance. I tested that on physical machines, etc. And I'm running these two options. So this is buffered IO. This is unbuffered IO. So what we're saying here is write block size of 512K and 1020 and write it 1,000 times. Here is 256K and 1,000 times. I do it with direct IO. So you can see the results. They're writing 8 gigabyte with 128 kilobyte, and with buffer it's 1.7 gigabyte per second, which is amazing. It's unbuffered, it's this. It's not even a joke. This is bad. But you know what? This is what happens when you run one. What happens when you run it in parallel? So here we are running 8 parallel instances of the same behavior. And you can see how it works. If I'm using unbuffered, if I'm using a large writes and parallel, I'm getting this number, which is absolutely amazing. Right? This is really interesting that smaller writes gave me a faster results here. Look at this number. For smaller writes, and this is not that small, you're seeing a huge drop in performance. In fact, I tested that a lot. And look at those numbers. This is making durable writes at a time. And this is the difference. When I'm writing 16 megabyte for each write, I'm hitting this guy. Writing 16 kilobyte, I'm hitting this guy. This is just, sad. What's going on? It turns out that there is a fixed cost for those durable writes. The smaller the write, more expensive it is to do that. I like to use the example of driving to the grocery store. It doesn't matter what you get from the grocery store. What matters is how long it takes you to go there. So if you go and say, oh, I want to get a pen, or if you want to get, enough food to last you a week, both of them would take roughly the same amount of time, would use roughly the same amount of gas. It's the same thing for durable write, even when you're running high-end NVMe systems. So let's go back to the system and try to understand what's going on. We have hundreds of writes to the disk all at the same time. Each one of them is an independent writer. All of them compete for the same disk. We completely and utterly saturated the IO pathways, effectively created traffic jam, the disk. That's just horrendous. And I want to fix that. I need to understand how I can fix this and what's going on. So we introduced something called shared journals. And this is the path of data during a commit. So during transaction, we modify all of the data in memory. During the commit, we take this and write it to the journal. And this is how you actually commit a transaction. But what I end up doing is saying, oh, let's not do that. Let's do this transaction, commit, do all of the things that you have to do to write it to the disk, and then don't send that. Don't write it to the journal. Instead, write it to a shared journal. Take the data from any pending write and send it to the disk in one shot. So going back to this case, here's the database, here are the indexes. Take the data from all of them, merge that into one write to the disk. And the whole idea here is instead of sending individual pieces, now we aggregate and send much bigger chunks, which, as we saw, is actually far better from our perspective. So that's amazing. We send everything in one shot. We also have specific optimized system calls, write file gather and PWrite in Linux, that allow me to do durable write for multiple buffer into the same location. So there is a single writer, single system call, no need to merge buffer, no need to do anything. And we basically pack a huge bunch of items directly to the disk for it to operate. That has some impact. how do I recover from this sort of system? So remember, I'm not writing the journal because I feel like it. I write to the journal because I have to deal with recovery if I have a power outage. So, if I have a shared journal, I can just, correct everything to go to the shared journal. But that actually leads to a huge problems from our perspective. How do I know when to delete a journal when all of the indexes are done reading that? What happens if you disable an index that reference a shared journal? Will I never be able to delete that shared journal? And how do we coordinate according to multiple indexes, the database, etc.? How do you, if you delete an index without going to RavenDB, just, RavenDB is shut down, you go and delete the index manually from the system. How do I know about that? So the answer is that I'm not even trying to do this. Instead, what I'm doing is I'm using hard link. So on the right side, I have one file that I'm writing to the disk. On the other side, on the read side, when I create this file, I also link it to all sorts of different locations. So every index has its own independent file. All of them share the same space on the disk, but they have multiple file names. And then I can let the management of when to delete the actual journal data to the operating system, because it is able to handle that because it already needs to handle hard links. Another thing about this is that when we started thinking about it, you know what? I have it later. We talk about this later. So let's talk about what this means. So I have now a whole bunch of hard links represented the same file. I write to that from multiple transactions at the same time to get to the same thing. It actually led to a different sort of problem. You might have noticed that I'm trying to summarize to you, and I've been talking for just over an hour. I'm trying to summarize to you how the entire system behaves with regards to close to a year of work and optimization and things like that. So hopefully this is not too much of a data dump. But anyway, going back to, I have 100 indexes running at the same time, and all of them are filling the same file. For the file size that we have for journal is not unlimited. So every X amount of disk space, we will create a new file. Then we would have to link it to all of the different indexes. Now, typically, this is the behavior that RavenDB has forever and ever. But typically, each environment, each index, each database handle that on its own. Now, because there is a shared file, we are running through each journal a lot faster. That means that we have to link it to all of those indexes at the same time. And because on Linux, directory operations such as create file, link file, etc., are not durable, we have to call fsync on the parent directory. We also have to modify the Voron header file, which is also an fsync. So under load, we have over 200 fsync per second that killed us. The solution for that was twofold. First of all, we stopped trying to do durable writes on the file. So we stopped doing durable linking on the file. Why is that? Because I'm already doing a durable write to the journal file. So I also wrote an entry there that told it, oh, you're linked to this and that file. That handled this scenario. Because when running recovery, I first run the recovery over the shared journal. We just rewire all of those hard links. Then I run the actual recovery for all of the other files, all of the other indexes and environment that I have. The other aspect was that because I'm fsyncing the journal file, I don't need to fsync the header. So that dropped me from another reason why I have to call fsync. And that gave me a much nicer environment. And now I have only 1 or 2 fsync per second, but hundreds of those. Finally, look at what we have here. I have two lanes, at least, that I care about. I have journal writes, and the user wait for them to complete. And data file writes that happen in the background because no user is waiting for them. But this is Voron. What about RavenDB in general? Because now we have both, remember, the data file and all of the indexes. So for indexes, they're also running in the background, but user needed as fast as possible so the indexes would complete. They also have journals and data file. So the way that it works is that under load, a data file, meeting transaction, modifying document, etc., is using this model. It is its own and independent. On the indexes side, we are piggybacking as much as possible. In typical scenario, it means that whenever we write to the data file, when we modify documents, each one of those writes is about 75 kilobytes. Remember, this is the scenario where we write about 1,000 writes per second. At the same time, every writes to the indexes is about 30 megabytes. So we have these multiple lanes that are operating at the same time. We have fast operations that are running for writing the journals on the data file, and big throughput-oriented stuff for writing of the journals. And after that, we have the data writes for the for the indexes and for the database files. Okay, so now you can see how this actually works. We have this high throughput stuff, and high latency. Well, actually, this should be the low latency. This is where we actually care about the latency. This is for journals. And we have high throughput. We still care very much about latency, but not that much because we still want to aggregate multiple writers. And finally, we have the bulkier stuff where we pig about everything and use low I/O, etc. Okay, so we merged that in August. We intend to push that to production in Q1 of 2026. So that's a huge amount of testing that we are putting into that because there is a huge amount of work to change that. Observable changes from the perspective of users, not that much. The changes that I talk about right now do change the structure of the data. This is not a migration or something. When you start running 8.0, we would update the schema version, basically, the structure of the journals, etc., that we're running. This is really cheap, but it does mean that you will not be able to go back to the old version. That's one of the reasons that we are running such an extensive operations. And this is the impact. And this scenario that we talked about, we're talking about a move from 87 requests per second to close to 600. And latency, we saw spiked at 2+ seconds. Again, this is on a big machine with NVMe disk, and under 100 milliseconds for this to run. Again, 100 indexes, 1,000 writes per second, and still working really nicely. With that, this is the rough summary of what we have for RavenDB 8.0. By the way, we are very likely going to have quite a few additional changes in there. This is just the stuff that we need to percolate over a long period of time. I really like that this is something that you don't need to have, crazy complex setup or a really big performance requirement. This just, you're using the system and you're getting it to free your disk space for you, and you don't need to worry about compaction anymore. If you're on the cloud, the lead stuff, we automatically manage that for you. Everything is just so much operationally simpler now. And with that, thank you very much. And if you have any questions, I'll be very happy to answer those.
All right, I see that someone is typing on the chat, so you might get a question. Oh yeah, that's a thank you. So yeah, Wow, Oren, where do I even start? First, thank you so much in the name of whole community for this truly spectacular talk. We're very glad to be guided through all the nuances in the journey, and it was a hell of an adventure. It was super approachable and very valuable, so thank you. Also, thanks everyone who joined us for this evening. I think I didn't miss any questions yet on the YouTube or even on the Discord, but I bet questions will rise on the Discord after the event, like always. So feel free to ask Oren about anything on the chat. You can hang out with us there anytime. And if you're watching on YouTube, the link into the Discord is in the stream description or the video description, so you can join. Yeah. So once again, Oren, thank you. I think we can start sunsetting this session. Yeah, and I think that's it.
So thank you. Thank you very much, everyone. Goodbye.
Thank you. Bye. Have a nice evening.